Understanding graphs of motion is an important skill in physics. Sometimes the motion of an object is so complex that just understanding individual values or a formula cannot really give us a true sense of what's happening. Later in the year, we will talk about more complex types of motion, but for right now, we'll focus on uniform motions, such as constant velocity and constant or uniform acceleration. Let's take a look at these graphs for an object moving with constant velocity. There are really three different objects represented on each of the graphs. Something that has a constant velocity has no acceleration, but the actual value of velocity can of course be very different. You can see how the acceleration graph, the final graph, has just a horizontal line right at the 0 point. That is going to be an indication of constant velocity. There is no change to the velocity. We can also see that constant velocity by looking at the velocity versus time graph. Here we see just a horizontal line, but now it is located at the value of the velocity. So the top graph represents an object going fairly fast in the positive direction. Then the graph below that represents an object moving again at a constant speed, but at a slower constant speed, but still in the positive direction. And then this object here is one that would be traveling in the opposite direction, maybe to the left at a very slow speed. These graphs can also, or these motions can also be represented on a position versus time graph. So this line here would represent the first object, something going very fast in the positive direction. Notice how the slope of this line corresponds to the value of this. So here we have a positive smaller value, and so that would correspond to this graph right here. Okay, so that would be the graph of x versus t for something going in the positive direction but slightly slower. Notice how we really can't tell anything about the initial position of the object from this graph. All this says is how fast it's going, not where the object is. All right, and then this last one here we have a negative slope that corresponds to a negative velocity. Again, this object could start in the positive area, the positive at a positive position, and move to a negative, or this line could be moved up here. It really, the actual placement on the graph cannot be really matched up based on the velocity graph. All right, let's take a look at uniform acceleration now. All right, so here again, I'm going to start with the acceleration graphs because those are usually the simplest. So if something has a uniform acceleration, then you're going to see a constant value of a, meaning a horizontal line at whatever that acceleration value is. So let's start with this object here. This object has a high positive velocity, a high positive acceleration. Okay, so that means that its slope over on this graph needs to be positive. All right, well, there's only one graph or one line that corresponds here. Notice that this is a straight line. That means that the acceleration is constant. The velocity is changing in a consistent way. The way that looks on a graph here is that the slope needs to be positive and it needs to be changing again in a gradual way, okay, but not constant in the sense of a straight line, but consistently changing. This graph here corresponds to this graph here. And this graph here. All right, well, how about this graph here? This is something that's moving in the positive direction initially, but then its slope is getting smaller and smaller. So its slope is decreasing. That means its velocity is decreasing. That would match up with this line right here. something that was initially moving in the positive direction, so positive v, but then its v keeps on getting smaller and smaller and smaller. Eventually it seems to stop because this value of v is 0. And you can see this line kind of veering off till it would have 0 slope at this point. All right, so this is a negative slope on the v versus t graph, so there would have to be a negative value acceleration over here. So it's going to be one of these two values. And comparing to the other line, this is a shallower line, and so that would be the smaller value acceleration, this one rather than this one. All right, our last example is something that has a negative acceleration, but it started with 0 velocity. Okay, that's what this is showing us. There's 0 slope, 0 velocity to start with, and then the object actually begins to speed up, but in the negative direction. Okay, this might be a ball that's been dropped, for instance. So that's shown here as well. The value of v is 0, and then it keeps on getting bigger and bigger, but in the negative direction. Right, that's a negative acceleration. Negative slope on this graph gives us a negative value on this graph. So that's probably the most important thing to recognize, is that there's a connection between the slope of one graph and the value of the next graph. The slope of this graph and the value of this graph. Okay, there are a few more complex things that we can take from these various types of graphs. Again, the position graph, velocity graph, and acceleration graph, all versus time. Let's first look at average values. This usually is going to be discussed in terms of the position versus time graph. A lot of times we will talk about an instantaneous velocity versus an average velocity. So let's take a look at what that would look like here. So the blue line is a line that's tangent at the time 5.5 seconds. That the slope of that line would correspond to the instantaneous velocity at that moment. The red line is corresponding to two different points. It's showing us the average velocity between t equals 3 seconds and t equals 8 seconds. Okay, so the object doesn't have that same value of velocity during that entire interval of time. It's just saying on average that is the velocity that it had. Whereas the blue line, the tangent line, is associated with a very specific moment in time, and that's what we call that instantaneous velocity. We'll talk more about these ideas as we get into our calculus discussions later in the year. Another idea that we want to understand is the meaning of area. And although area can be discussed on any graph, the one that we discuss most is the area on a velocity versus time graph. You should remember this from last year. We certainly discussed it. On a velocity versus time graph, the area would be calculated by taking meters per second as your height and seconds times seconds as your base. So meters per second times seconds leaves you with meters. It gives you a value of displacement. So just one thing that we kind of need to watch out for is that if the area is below the horizontal axis, below the zero velocity point, that's meaning that the object is moving backward. Okay, the velocity is negative, the object moves backwards, and so the displacement is negative. Whereas this red section here shows us an object moving forward. And we could figure out exactly how far the object moved forward by just calculating the area of that trapezoid, making sure that we pay attention to the scale on the graphs. Now this can be done for an acceleration graph. It's just not very, very common. An acceleration graph, you would be taking meters per second squared times seconds, and that would leave us with meters per second. So it corresponds to a change in velocity, but again, that's kind of a rare thing for us to be doing. Another key skill having to do with graphs is a turning point. Okay, and so a turning point is going to be a spot where a very smooth curve just changes direction from going from the top of the graph to then going to the bottom and then back up again, or in reverse. You've probably talked about this idea in a math class. If you take a look at the position versus time graph here, at 7 seconds we have a turning point. Okay, it's a very crucial point in the object's motion. This is where the slope on this graph would momentarily be 0, and so that means our object stops just for an instant. Maybe it has bounced, maybe it's hit a wall, maybe it's been thrown in the air. Just for some reason it has stopped for a split second. And you can see that in the second graph as well. This is, again, remember the slope on the position graph tells us the value on the velocity graph. And so at 7 seconds, the value of the velocity is 0. All right, last skill here very quickly. We just need to make sure we understand what positive and negative values mean on each of these graphs. So on position graphs, a positive value means the object is located to the right of the origin, or if we're working vertically, it's maybe above the ground, something like that. And negative values mean you're to the left. And so you got to remember that position graphs show you positions, and so that's what the positive and negative would refer to. On a velocity graph is showing you the actual motion of the object, the value of the speed and which direction it's moving. So positive values of velocity mean the object is moving in the positive direction, say to the right. So like this object here, we can see from the top graph that it starts at 4 meters, it moves backwards to 0, goes all the way to -3, and then comes back again. So you can see again that at the 7-second point, that's where the direction of its motion changes. But all the way up to there, it's moving to the left. And that's what this graph shows us as well. Negative velocities all the way through here. The object is moving to the left. And then at this point, where this graph starts to head back toward the positive direction, okay, it's moving to the right, here we have positive values of velocity. Okay, so that does kind of correspond to each other. Acceleration graphs, same sort of a thing. The value, though, on an acceleration graph tells you which way the acceleration points. And that can be kind of tricky because an object with positive acceleration that moves in the positive direction, yeah, it's speeding up. But if it has a positive acceleration and it's moving in the negative direction, it actually is slowing down. So this is something we're going to have to spend some time working on. We'll probably talk about this graph specifically in class, but you can see that between 2 and 4 seconds, this object has negative acceleration and it's moving in the negative direction. All right, so that means it speeds up. But then for a short time, between 4 and 5 seconds, it stops speeding up, okay? It stops accelerating. And so it maintains its velocity between 4 and 5 seconds. Then from the acceleration graph, we can see that the acceleration now is positive during the next few seconds here. But the object is moving to the left, and the acceleration points to the right. So that causes it to slow down. Doesn't mean that it suddenly turns around. It just means that it slows down. And we can see that on the velocity graph here. The value of v is getting smaller, but it's still a negative value. Okay, it's still moving to the left. And then notice when the object stops for that split second, that turning point, doesn't mean that the acceleration has to be 0. Okay, the acceleration is just talking about the change in the velocity. And the velocity is still changing at that moment. And so it can continue. So acceleration graphs are a little trickier. We'll have to kind of watch out for those.